I think we are done for today's module makers presentation. And now we are going to enter into the materials field. We have Imco Goudswaard, who is a commercial manager at leading material supplier Endurans. And Imco is going to talk about reliable and future-proof Coextruded polyolefin backsheet and encapsulation solutions. Imco? Yeah, we could see it.
Okay. Good. What I will do is shed some light on the module reliability from encapsulation and backsheet perspective. We see a lot of cost pressure, and main question is whether we can still fulfill all the requirements despite this cost pressure. And we'll show that from the perspective of Endurans Solar. Can we go to the next slide? Just for those who don't know Endurans Solar, we are US-based backsheet and since this year also encapsulant suppliers. We have manufacturing in the US where we manufacture our polyolefin-based backsheets, and we added this year also encapsulants to our portfolio, both single-layer encapsulants like EVA or POE, and also a new EPE, so a multi-layer encapsulant. Okay, next slide. Our expertise is mainly in polymer technology. We make use of extrusion both for backsheets and encapsulants, of course, and we also formulate our own compounds in contrast to standard backsheets, which make use of pre-produced films. Like I said, our manufacturing is in the US. We are a leading supplier in the polyolefin backsheet field, and we have a whole pipeline of new projects where we work on to meet the upcoming requirements of the PV industry. Next slide. So zooming in on the backsheets, and knowing that cost has reduced, as you see on the left side. What happened for backsheet to follow this cost curve, you see on the right side, and it's not really a big change in design. It's mostly reducing the most cost expensive component of the backsheet, which is the outer layer of the backsheet in contact with the air or the outdoor environment, and that mostly is a fluoropolymer film, and it's there to protect the core polyester layer of a backsheet. Polyester as such is a strong, low cost and also electrical insulating material, but it's not, well, I would say not suitable for outdoor application because it easily hydrolyzes. So you either fill it completely with stabilizers, or you use, like the PV industry does mostly, you use a fluoropolymer outer layer, which is highly inert and can resist all the outdoor loading and protects the PET layer. But what happened in the let's say past 2 decades is that where we started from a backsheet with a Tedlar fluoropolymer film on both sides of the backsheet, we gradually, forced by cost reductions, reduced the thickness of the Tedlar layer. Then we replaced one of the Tedlar layers by a cheaper fluoropolymer PVDF. Also reduced that thickness again, and at the end we ended up with fluoropolymer which is just coated like a 10 or 50 micron layer on top of the polyester. So that really shows you that due to the cost, the backsheet industry has compromised on quality, because this fluoropolymer is there to protect the polyester core layer. Now that you could say is like kind of dead-end street, and that's what we saw about 15 years ago, and we started thinking about how can we circumvent this and make a stronger but still affordable backsheet. Next sheet, please. So how can we make it future-proof? And that's where we came up with the coextruded polyolefin backsheet concept, which actually ticks all the boxes which are relevant for a future-proof module. So first of all, that's cost and availability. The polyolefins are the largest group of polymers available, and by use of co-extrusion, we skip the intermediate step of producing a film, which is used in the traditional backsheets and laminated together. And on reliability, polyolefins are highly inert and also strong like polyesters. I always like to give the example of the roof membrane used a lot in Europe, which is also made of polyolefins, and in terms of loading, it's very similar to what backsheet experiences. So there's a lot of UV light, there's thermal changes, freezing or high heat, there's rain, there's snow, so everything comparable to what happens with a backsheet. And also in roof membranes, this is a very proven material concept. And next to that, polyolefins also have a favorable breathing barrier properties, which means that they have a high water barrier or moisture barrier, and they easily let acetic acid pass. So any degradation product from the EVA migrate out easily during daytime. And last but not least, sustainability is also a very important requirement, although there's not so much attention yet for that, and also not in standards or requirements, but it's upcoming, and we also took that into account in design of our new backsheet concept. And the advantage of polyolefins there is that they are thermoplastic, so you can just remelt it, and at the end of life or after for production waste, the carbon intensity is relatively low, especially compared to glass, for instance. At the end of life, you can either regain the energy in an energy to waste to energy facility, or you can even enter it in a pyrolysis process where you get the monomers back with an efficiency of almost 90%. Next slide. What I will do for the rest of the presentation is illustrate this strength of the coextruded polyolefins by giving you two examples of products which we are soon to launch. One of them is a transparent backsheet for bifacial modules, and the other one is an EPE encapsulant. Okay, next slide. First, the transparent backsheet. Yeah, next slide. So this is the solution where we came up. It's based on our well-known HPO, so the coextruded polyolefin technology has all those advantages. It's proven both with PERC as well as TOPCon passes IFC standards, and also PVAL PQP. And what we added to that technology is a light trapping technology. What you in the market, you see either transparent backsheets or glass being used, often with a mesh, but the mesh is or the cell gaps are getting thinner and thinner, so the added value of that mesh is also reducing. And another thing is that light from the rear is always diffused, and in a just fully transparent backsheet, the light trapping of diffuse light is not optimum. So that we change, and I will show that in the next slide. By leaving out that mesh. Oh, sorry, no. Can we stay to the previous one for just a second? Yeah. So I want to say, without using the mesh, it's much easier to handle in production. So there's no positioning. We can supply it on the roll. And being a polymer backsheet, of course, that also has a weight advantage over glass. Also circular by design. It's transparent, so also does not contain any titanium dioxide anymore. It has the lowest carbon footprint because of that available in the market at this moment, and it's 100% recyclable. And for our American customers, of course, it's important that it's produced in the USA, so it supports the IRA there. Okay, next slide. This is the light trapping effect on the left side. This is about light coming from the front. Like I said, the cell gaps are getting less and less. By including some reflection in our backsheet, we still have a good result in the front side flash test. But the main difference is obtained by making the film hazy, so it gets a diffuse transmission, and that is beneficial for the light which comes from the rear, because light from the rear never gets perpendicular. It's always scattered, diffuse, and with this high diffuse transmission, the light trapping effect of the film is much higher compared to a fully transparent backsheet. Next slide. This is some development results we did on just purely the film, so not laminated yet. It's aged under different circumstances, UV, humidity, pressure cooker test. Then you see that we always look in this case does something change in the polymer structure, and that's best shown by the irrigation at break. And you can see here that after these aging periods, we had a reduction of, well, let's say something like 20%, which is very much acceptable. And on the right side, we also optical properties, of course, are very important, and we did the same aging tests on the samples and checked on optical performance, where there's also little change in or still a lot of retention after these aging times. Next slide. And this is for the laminated samples. So we laminated the transparent backsheet and tested EVA adhesion, retention there in damp heat. And on the right side, we made mini modules with just one cell, and we checked also the degradation after damp heat and combined damp heat UV, which is still far beyond within the limits of which is acceptable. Next slide. And then, this is, let's say, the proof of the pudding on the light trapping effect. On the left bar, you see the flash test result of a full-size module, a TOPCon module, where we, due to the somewhat higher reflection all over the surface, we get a slightly higher output, but that's minimum. And the big difference is when you put these modules in the field. On the right side, you see a picture. These have been positioned in Arizona on a tracker and used the tracking system, but also used fixed tilt. And on the right graph, you can see that the additional power output is increased by, well, let's say roughly 3%, depending whether you use a fixed tilt or a tracker. So that's the main advantage of the light trapping concept. Next slide. Yeah, then we go to the example of the encapsulant. Well, this is probably a known story about what functionalities an encapsulant should have. It's like a cushion for the cells. It must be a barrier, and it should have good adhesion to the glass and to the backsheet. Next slide. So we developed an EPE, and EPE you could consider as an encapsulant which combines best of both worlds of EVA and POE. But there are also some compromises where not best of both worlds, and that has to do with that there's still asset formation and also cost of the EPE encapsulant is, yeah, I would say kind of compromised a little bit in the middle of these two. So we especially worked on these compromises we found. Next slide. And what we did is we replaced the expensive core layer, the POE, the cross-linked POE core layer, by a high melting polyethylene, and that has a couple of advantages. First of all, you increase the moisture barrier, which also has a reducing effect on acid formation. The film itself is also much stiffer and also has a lower shrinkage. So in terms of cell shifting and handling, that makes it easier. Because of the lower cost, also the cost of the PE core layer compared to a POE, also costs will be lower. And last but not least, sustainability, because of the core layer not being cross-linked, that enables a module maker at the end of life to easily, by a thermal treatment, disassemble the glass and the backsheet from the core layer with the cells in which the high value products are more easily available when compared to a backsheet where the encapsulants are cross-linked. Okay, next slide. Here's some data. This is with respect to the water vapor transmission rate. On the left side, you see relatively high rate for EVA, and then significantly lower for EPE and POE, which are close together. And then by changing the POE core layer, we get a further 40% reduction of the water vapor transmission rate. Like I said, which also will have effect on acid formation. Next slide. Also, this is another example of the impact of the higher water barrier or moisture barrier. Will affect also PRD performance. On the left two bars, there is a module with two EVAs. When you change one of the EVAs by EPE, still you don't get much of a gain, but you really see the difference in leakage currents when both EVA layers are replaced by this EPE type of encapsulant. Slide. We often get is, yeah, your core layer is not cross-linked, doesn't start to creep. So of course we did a lot of creep tests there and did vertical two glass plates with the encapsulant in between. We put that in the oven for 200 hours and measure the displacement at 105 degrees C. And we did not measure any displacement. So the temperature resistance is high enough for the PV module application. Next slide. Here, of course, for encapsulants, the optical properties are very relevant, and especially stability under continuous UV light, and that's what you see here, up to 5,000 hours UV exposure, where there's no change in transmission. So, which proves it's a very stable product. Next slide. That is the last one. So in summary, it's clear that we're by choosing the design concept of coextruded polyolefin backsheet, we are able to meet the let's say increasing requirements under increasing cost requirements in terms of cost and availability, in terms of reliability of the module, and also in terms of sustainability. I think that is the last one, so that concludes my presentation. Happy to answer any questions, Saran.
Thanks, Imco. That's a very nice presentation. So, you know, one question I have is, you said your backsheet doesn't need any grade. So, and it's also not completely transparent. So, you know, what is the transparency when you compare to glass or any transparent backsheet? But what is the overall energy gain? So I think I saw in your presentation, you mentioned somewhere around 3%. So have you considered everything, you know, an apple to apple comparison between a transparent backsheet and your backsheet? So this is what it is. Can you just throw some more light?
Yeah, so just I think transparency of glass is something like 92% of let's say commercial transparent backsheet. That probably goes up to 82, 83%. And due to the haze we add to our backsheet, we get to a transmission of something like 78%.
And so there, still you have the overall power yield of 3% higher than the transparent backsheet.
Yeah, with that correct. So that has mainly to do with the rear side impact. So from the front side, we still have some reflection even if we don't have a grid. And of course that really depends on what is the cell gap. So the smaller the cell gap, the lower the added value of a grid is. So then it will be clear. But when you make your we didn't test, but I guess if you make your cell gap something like 4%, so 4 millimeters, then you will have a huge effect of that grid, of course, on the front side. But the gain is on the rear side because light from the rear is diffuse, and if you have a fully transparent glass or polymer transparent backsheet, then your light trapping is less, so you get more reflection on the surface on the different angles. So your low angle incident rays will be reflected and not go towards the cell. Well, if you have a little bit of haziness, you see that diffuse transmission is going up in your film, and that captures the light also under low angles and gives you more output. And that's the 3% you see in the field.
Perfect. Okay, thank you. So if there are any questions in the chat window, please try to answer them. Stay tuned till we meet again for the panel.
Thank you.
Great.